Hello and welcome to my talk on the deep parametric PDE method for option pricing. In this talk I will show how we can use deep neural networks to solve problems in finance. After discussing the motivation of our work, I will briefly introduce deep neural networks. Then I will go on to introduce the deep parametric PDE method for option pricing and present an example from exposure calculation. The motivation of our work lies in the growing regulatory pressure which financial institutions are facing. Regulators require banks to provide a more complex risk analysis, which includes frequent calls of a pricer. They require the use of scenario calculations, which needs the use of different model parameters, and they demand a higher precision, which excludes crude simplifications that were once acceptable. This means that we need derivative pricers which are fast for a whole range of parameters, reliable, and able to tackle high-dimensional problems. And in this talk I will show how deep neural networks can help us to meet these requirements. The deep parametric PDE method is based on the observation that deep neural networks are highly efficient at approximating high-dimensional functions. This was first seen in supervised learning, where neural networks can solve problems with hundreds to millions of features. For us, this means that the dimension of the problem is no longer limiting us, and we can approximate the price for any time, state, and parameter value at the same time. You can find a preprint of our article on arXiv, and I made a code available on GitHub if you want to give it a try yourself. Let me briefly introduce deep neural networks. As mentioned, they became popular due to their enormous success in machine learning, where they efficiently handle high-dimensional data. In a nutshell, neural networks can be considered to be a successive application of an affine transformation and a fixed nonlinear function, which is applied element-wise. Hereby, the weights of the transformation are variable and will be adapted to the problem at hand. In the following, we interpret the network as a function which maps the values from the input layer to the output layer. The input layer will consist of the time, state, and parameter values, while the output layer will approximate the option price. The aforementioned weights parameterize this function. To solve our option pricing problem with neural networks, there are two basic approaches, considering a supervised learning problem or an unsupervised learning problem. With an unsupervised learning approach, we treat the problem like a model order reduction problem. We calculate a training set of prices using a reference pricer and then set up a standard machine learning problem to approximate these prices. The issue here is the dependency on the reference pricer, which needs to be implemented fast enough and accurate enough. For high dimensions, this can be highly restrictive. Instead, with an unsupervised learning approach, we directly solve the problem. The key step here is to reformulate the problem as a minimization problem over some function space x. Then we can replace the function space x by the set of neural networks, which is parameterized by the network parameter theta. This way we are independent of the availability and the performance of a reference pricer. Our way of reformulating the parametric PDE as a minimization problem is based on its least squares formulation. Let us consider a high-dimensional parabolic PDE, which is to be solved for each parameter value. We take the square of the PDE's residual and integrate it over the time, space, and parameter domain to obtain the loss function, which is to be minimized by a neural network. Now, to summarize the method, there are two distinct phases: a one-time offline phase and the online phase. In the one-time offline phase, we train the model. This requires us to set up the residual and then to optimize the network parameter theta. Both steps require derivatives of the output with respect to different variables. These derivatives can be evaluated by a backpropagation of the network. This training phase is computationally challenging, but can be performed at idle times, such as at night or over a weekend. Once the network is trained, a simple forward pass of the network allows us to quickly evaluate the option price for each time, state and parameter value of interest in the matter of milliseconds. Now let us revisit our initial motivation, an increased regulatory pressure regarding risk analysis. And one particular risk is the counterparty credit risk, which is the risk that your counterparty defaults and is unable to deliver the underlying assets at maturity. One part of quantifying the counterparty credit risk is the calculation of exposure, which analyzes the loss in case of a default. The expected exposure is the expected positive value of the derivative. This is the expected loss in case of a default if there is no risk mitigation. We also consider the potential future exposure, which is a quantile of the price distribution. It gives us a limit such that in the best, say 95% of our cases, our loss would be lower than this value. A standard technique to evaluate exposures is the full revaluation using a Monte Carlo simulation. Here, for a number of simulated paths, the option price is evaluated and the mean or the quantiles are computed. It is important to note that the Monte Carlo simulation is not used to evaluate the derivative price, but for each simulated path we call the solver. Thus it is easy to see that the computational cost of the pricer is dominating the overall cost. In our case, 150,000 of these evaluations are required. The results for the simplest case, for a single asset option, are shown on this slide. This case is only to evaluate the accuracy of the deep parametric PDE method, as we can compare our method to the exact Black-Scholes formula. In the two plots, we see the expected exposure on the left and the potential future exposure on the right, both calculated with the deep parametric PDE method and with the exact Black-Scholes formula. I'd like to point your attention to the left figure, the expected exposure and the risk-free measure, because we know that in this case the exposure is constant and it is equal to the option price. This means that we can identify the error on the exposure by any oscillations of the two graphs. Since the Black-Scholes formula is exact up to machine precision, the only error source is the Monte Carlo simulation during the full revaluation. The deep parametric PDE method shows a similar error to the Black-Scholes formula, which means that the pricing error of our method is negligible in comparison to the Monte Carlo error of the full revaluation. This shows the suitability of the method for this application. Let's now have a look at runtimes in situations of practical interest. The case of a basket option with two underlyings is already more interesting, as there is no analytic pricing formula anymore. Instead, we compare the deep parametric PDE method to two cases. A crude simplification, where we have fitted a one-dimensional Black-Scholes model to the two-dimensional process, and a reference pricer, which is based on the one-dimensional integral. The crude simplification yields an extremely fast result, but is highly unreliable. And even though the reference pricer is only based on the one-dimensional integral, it is still quite slow and we had to reduce the number of Monte Carlo paths to limit the runtime. It still took longer than the deep parametric PDE method and showed a larger error. Only the deep parametric PDE method was able to compute an accurate result in an acceptable time using 5.5 minutes. A basket option with 8 underlying assets confirms these results. While the deep parametric PDE method has a stable runtime and a stable accuracy, the reference pricer took in practical 10 hours to compute 1000 values. Note that due to the parameters of the problem, the deep parametric PDE method has to solve a 25-dimensional problem, which it does without any issues. And with these results I would like to conclude. We have seen how the deep parametric PDE method uses a single neural network to approximate the option price for all time, state and parameter values at the same time. It uses unsupervised learning based on the least squares formulation of the PDE, which means that it does not require a reference pricer. Despite the high dimensionality of the problem, we have seen small errors and fast evaluations, which led to a strong performance for exposure calculations. If you want to try for yourself, there is a preprint on arXiv, there is a code on GitHub, and I will be available for questions and comments during this conference. Thank you very much for your attention.